Yes, I'll wait for somebody to tell me you can't, but I assume you can. And Edith asked me to get this done in 13 minutes, so I'm going to start. So I want to set the stage for where we are and how far we've come. If you look at the two photographs here, the photograph on the left was taken in the year 1900 in New York City, and you can see two modes of transportation. You can see humans are either walking or humans are using horse and buggy. If you look at the photograph on the right, taken only 13 years later, there's no more horse and buggy. Everybody's driving a vehicle that is an internal combustion engine. If we think about how we used to farm, the image on the left captures what farming was like in the late 1800s, when everything was done by manual labor, and it would have taken 25 men a full day to harvest and thresh a ton of grain. Compare that to the photograph on the right, where we can use GPS-navigated combines. We can farm the same amount of land in 6 minutes, and we only need 2 humans involved. Life expectancy has changed radically. In the last century, life expectancy has doubled globally, doubled. And that's because we have significantly improved healthcare options for people around the world. We're not perfect yet, but we're far better than we were. When we look at global population, top right, we've gone from about 1.5 billion people in 1900 to now we're pushing 8 billion people. If we look at the bottom right, we can see that economic productivity or economic output measured by the most commonly used concept, gross domestic product, that's also increased significantly over the last century in lockstep with global population. Global population and increased economic output, without any doubt, have increased in direct relation to fossil fuel consumption, which is now plotted here top right and bottom right. The Industrial Revolution was powered first by coal, then oil, then natural gas, and our consumption of fossil fuels and all of the things that we use them to do for us have radically altered humanity. Now, we know that we can extract energy from fossil fuels, such as coal, oil, and natural gas, through this really simple reaction that we call combustion, where the example I'm showing here is 1 molecule of methane, which is a carbon atom surrounded by or bonded to 4 hydrogen atoms. If we react methane in the presence of oxygen, that liberates energy stored in the bonds within the methane molecule, so it's an exothermic reaction. And it also releases carbon dioxide and water as byproducts of that exothermic reaction. When we look at historical consumption of coal, oil, and natural gas, collectively we have really good data for exactly how much of each fossil fuel we've used, and we can simply mass balance the total amount of coal, oil, and natural gas that we've combusted, and we can come up with this red line here, which is the calculated carbon emissions from all of the combustion of oil, coal, and natural gas since the Industrial Revolution. Now, in 1982, scientists working for Exxon, they used historical carbon emissions data to predict future concentrations of CO2. This is commonly what scientists do. They were particularly interested in predicting how much CO2 our future atmosphere would have if we as a society continued to combust coal, oil, and natural gas at a rate consistent with historical rates. So they looked at the concentration of CO2 that was 316 parts per million in 1960. They knew that the concentration of CO2 in 1980 was 338 ppm. And if you look at the plot on the right side of the screen, you can see that annually from 1959 to 1983, carbon emissions went up systematically every year. Well, Exxon scientists, they looked at those data and they predicted that in the year 2020, the atmospheric concentration of CO2 would be 415 parts per million. And boom, they were spot on. So now I've added to this chart all the years through 2021, and you can see each of the blue circles is the global average CO2 concentration of Earth's atmosphere. And you can see that the Exxon scientists were incredibly smart. They got it exactly correct. Now, those scientists at Exxon, they also understood what we call the greenhouse gas effect. So they knew that increasing abundance of molecules of methane and carbon dioxide and water, which is not shown here, that as the abundance of those three gases increased in the atmosphere, that would result in trapping long-wave radiation re-radiated from Earth, and they predicted that would cause warming of Earth's atmosphere. The plot on the right is from their actual internal study, and what you can see on the left y-axis is atmospheric CO2 in parts per million. On the right side is the average temperature increase, and then the bottom is time. So we can look here at the black arrow, and in 1982, what the scientists at Exxon did is they forecasted or predicted that by 2020, CO2 would be about 415 parts per million. It's exactly what it was in 2020. And that would result in an average global atmospheric temperature about 1 degree higher relative to 1960. Well, guess what? Their prediction came true. So now we're looking at time on the x-axis and temperature change relative to 1960 as the baseline year. And you can see that in 2020, the average temperature is 1.21 degrees warmer than it was in 1960. It's amazing how well science works. So following the protocol or the methodology that ExxonMobil used, sorry, that was just Exxon then, we can actually project out that the red line here shows us if we continue to combust fossil fuels at the same rate that we're using them today, and we continue to see increased combustion of fossil fuels in markets globally where the penetration rate of everything that we use fossil fuels to do, as that increases, if we continue to allow emissions unabated, by 2100, average temperatures will increase by 4 degrees. Now, a lot of people hear that and say, who cares? What does that matter? Well, we're experiencing why that matters. So this is a snapshot over the last few years of cities around the world that have seen record high temperatures. And we're seeing that importantly in agricultural yields. So this is a global map that shows you all the areas where corn is grown, and anything in orange and red means that by the year 2070, crop yields will decline by 20 or more percent. That's not good with an increasing global population. So how do we keep those temperatures from getting 4 degrees higher relative to 1960? Well, that's shown here in this teal line where it finishes at 2100 next to substantial cuts in emissions. So how do we do that? We have to electrify everything. No more combustion of fossil fuels. Everything is electric. And in order to achieve net zero by 2050, that requires 90% of global electricity generation comes from renewable sources, where solar photovoltaic and wind turbines account for about 70% of all global electricity production. Now, can we do it? Absolutely, right? When we look at the pledges here made by various auto companies and the state of California, companies, they see that people want electric vehicles and they're responding to that consumer demand. California requires by 2035, 100% of all vehicles sold have to be fully electric. And trust me, what California does, other states and other countries will follow because they're such a large market. So this is what I've done. I live in Ann Arbor, Michigan, 42 degrees north latitude, and yes, our winters are cold, and yes, our winters are sort of dark, but I built a solar array in my backyard, and I've got, in the middle photograph, 6 batteries here, lithium iron phosphorus batteries, and on the right-hand side is a picture of my living room and dining room where I'm circling our heat pump that we use to heat in the winter and cool in the summer. And my wife and I share an electric vehicle, and every day when she comes home or I come home or we come home together, we just plug it in. We're fully self-contained. We don't need any energy from anyone else because we're generating everything we need. Now, some people are going to question that, but trust me, it works. So these are data from my house yesterday, August 27th. This is the electricity I used, varied over the course of the day. And you can see that during the morning hours, midnight here, bottom left, my battery was used when the sun isn't shining. Then the sun comes out and you can see this huge peak in solar electricity production. And I'm recharging my battery during that time because the green line here, which shows how much electricity I'm using a lot less than I'm generating during the afternoon. We've modeled this for the entire state of Michigan. So here, top left, the state in red is Michigan, the lower peninsula and the upper peninsula. And if you look at the image on the right, this is a map that shows you in pink for solar and gray for wind, utility scale wind and solar. If everything is electric in this entire area of Michigan, everything, all of our trucks, all of our cars, everything except for airplanes, everything is electric, including heat, that's the land that we need. It's not that much. Now, there's a lot of criticism about the inability of solar to provide electricity at night and the inability of wind turbines to provide wind when it's not windy. Absolutely true. That's where grid scale battery storage comes into play. And already we're seeing the price of grid scale battery storage is lower than traditional natural gas peaker plants. So what does all of this require? Right? It sounds easy to say electrify everything. Well, what it requires is a lot more of the metals, some of which are pictured here, for solar, for wind, and for battery electric vehicles. A lot more of the metals that we currently use, but in order to hashtag electrify everything, we need to significantly increase their production. Now, fortunately, I live in an academic bubble in Ann Arbor, Michigan, so we've got an Ann Arbor solar tree farm where we can go down and just pick the panels. Hopefully some people snickered there. No, what this requires is lots of mining, right? When we look at an open pit such as the one shown here, and this is an open pit where copper is being mined, and copper makes this particular mineral deposit economic, in order to achieve carbon neutrality, net zero, by building wind turbines, building solar panels, and electrifying our global transportation fleet, we've got to mine. If we look at the current projections for the metals copper, lithium, and cobalt, all I want you to see for each of these, if I highlight for copper, is right now, if we look at all of the operating copper mines, and we project out to 2030, 2040, 2050, we are not going to be able globally to supply the copper, lithium, and cobalt that we need for a net zero world. The same is true for lead, manganese, chromium, zinc, silver, silicon. So this y-axis is the ratio of supply over demand, where supply is the forecasted production from either operating mines or mines that are being constructed now. And for each of these metals, the supply-demand ratio is less than 1, which means we can't build the renewable energy infrastructure that we would need to achieve net zero. We also have the challenge that the average length of time from a mineral resource discovery to actually producing metals from that deposit, it exceeds 10 years, which means that if we want to achieve net zero by 2050, we've got a really short window to do that. This requires a real change in the mindset of everyone. We have lots of people around the world that advocate for renewable energy, but we experience a lot of cognitive dissonance where people are opposed to mining. So this is my last slide, and it's my call for everybody in the audience, no matter where you work or who you engage with, it is critically important that society as a whole appreciate that we need to increase rapidly the time it takes to permit new mines. We need to get more mines up and running to produce the lithium and nickel and copper and rare earths that can make our world net zero by 2050.